Okay, time to jump into the force unit. That means we need to look at the man, Sir Isaac Newton. And he has 3 laws of motion, but we'll find out they all have to do with force as well. First law! All right, so the first law is often called the law of inertia. It basically just states that an object at rest stays at rest, an object in motion stays in motion, unless an unbalanced force acts on them. Okay, so that seems simple enough. But you might be questioning, why do I need to know this? I learned what this meant a long time ago. Well, you need to understand that motion is a direct relationship with force. And because of that, we need to understand that there are forces constantly acting on everything around us. We're going to learn a bunch of different types of force. Some can act at a distance, some have to directly touch it. So think about Newton's first law this way. So you go to the bowling alley, you throw your ball, you apply a force to it, and it moves along, and it crashes, and the friction, or the force of hitting the balls, stops it, or allows it to go through, and then the wall stops it. But there's still things that stop it. There's things that started the motion. You pushing on it started it moving, right? There's friction, even though that aisle is very slick, and that's why they keep it that way. So there's less friction, and it's rolling, so it's not a lot of friction anyway. We'll find out. But then there's a lot of friction when it does hit the pins, because that's forces directly acting back on it. And all of that is a force. So these are forces stopping it. However, if you were to roll it in outer space, there's nothing to stop it. And so it would just go on and on and on and on and on and on and on forever, until it eventually hit a planet or hit a gravity maybe. But that's the gist of Newton's first law, is every change in motion we see is caused by a force. Now, inertia on its own is not considered really quantifiable. However, it is directly relational to mass of an object. So some fun things you can do with Newton's first law and to try out how that inertia works is try setting an index card on a glass of water with a coin sitting on the top of it. If you apply just a force to the index card to the side, it's not applying a lot of force to the coin, and so due to its inertia, it wants to stay. Thus, Newton's first law, an object in motion or an object not in motion, wants to stay not in motion, unless a force is acting on it. Since you're not acting on it, you're acting on the card. Most of the time, it will drop straight down. It's also the reason when we crash, we still go forward. We're already moving, and force acts on the car to stop it, but it doesn't necessarily act on us unless you're wearing your seatbelt, and so you want to go flying through. Second law. So Newton's second law, when appropriately stated, is the acceleration of an object is directly proportional to the magnitude and direction of the applied force, but is inversely proportional to the mass of the object. Say what? So all that really means is F equals ma. It's a mathematical relationship between force, mass, and acceleration. So if you think about this, he's just starting with acceleration equals force divided by mass. Acceleration is directly proportional to the force and inversely proportional to the mass, because the mass is on bottom. You can just think about it as this relationship right here, okay? All of them have a mathematical relationship to one another, and so we sum up Newton's second law is F equals ma. This makes sense if you look at things, because if you're going to do something like keep the acceleration constant, you're going to have to increase both mass and force in order to have this still balance out, right? If you're keeping the mass constant, you would have to increase both force and acceleration. But if you wanted to keep force the same and you increase the mass, you would have to decrease acceleration, or vice versa. So you would have to increase acceleration and decrease mass. It's basically just a mathematical formula that says force is equal to mass times acceleration. Third law. Now, I find that Newton's third law is everybody's favorite because it's the one that they memorize, and for some reason, it's the one that always sticks in their mind. And they almost always remember it when they're a little kid. And they go, for every action, there is an equal and opposite reaction. That's right. But what does that mean? So that's the problem. You memorize things, you never remember it. So here's a little bit idea of what that might mean and how it applies to things. So essentially, everything in life every time you have something that applies a force, some sort of action, you're going to get a reaction. A fun example of this is taking a balloon and blowing it up full of air. You're exerting a force, and it's being held by the elasticity of the balloon, and then you just let it go. When you let it go, it applies that force to air particles, but the air particles apply a force back on the balloon. So you get it moving around the room, and it goes always fun, no matter how old you are, to hear a farty noise and see a balloon fly around. Anyway, though, that is Newton's third law, equal and opposite reaction. Now, yes, there's motion in it, but there doesn't always have to be. So think also about somebody standing on the ground, right? Well, we know because of gravity that they have to be exerting a force downward, right? So there we have it. They're exerting their force downward on the ground. But they don't go through the ground because of Newton's third law. Because if they're exerting a force on the ground, then the ground is exerting an equal and opposite force on them. So why does the balloon move, but the person stays still? Especially if we think about this in regards to Newton's first and second law. Because the first law talks about for an object in motion tend to stay in motion, object at rest tend to stay at rest unless acted on by an unbalanced force. And then the second law tells us there's a mathematical relationship. So we really need to look at this just a little bit more. I like to do that by looking at the old hammer and nail scenario. So you have a nice hammer and you smash it onto a nail, right? Well, if you're smashing it onto the nail, what's going to happen? The nail's going to move, right? You're going to hammer the nail in. But according to Newton's third law, every time you hit that nail on the head, there is an equal and opposite reaction going on, correct? So that means that every time you hit the nail, that nail has to hit the hammer back with an equal and opposite amount of force. Equal and opposite amount of force, yes. And so we would create a Newton's law, or a Newton's pair. And so what we do is we say that this one is the force of the hammer on the nail. And then this one over here is the force of the nail on the hammer. Okay? And we actually can write this out just a little bit more mathematically. So you can see here we get the force of the hammer on the nail is equal to the force of the nail on the hammer. But that's not quite true. We also need these nice little lines that let us know we're just talking about a magnitude because a force is a vector, and that means it's directional, and these are opposite directions. They're just equal in magnitude. So we're saying that the absolute value of the force of the hammer on the nail is equal to the force of the nail on the hammer. And this is a true statement. But why does the nail move then? Well, it has to do with Newton's second law, which indicates that if this is true and these forces are equal, well, something else has to be true. If you have the mass of the nail times the acceleration of the nail has to be equal to the mass of the hammer times the acceleration of the hammer, right? Now, the forces are equal, but the mass is not going to be, so the acceleration is not going to be, due to Newton's second law, that the acceleration is directly proportional to the force, but inversely proportional to the mass. Meaning, as the mass goes up, like it does in the hammer here, the acceleration goes down. So if you hit the nail on with the hammer, there is an equal force, but because of the greater mass of the hammer, it accelerates much less in order to keep that an equal amount of force to the amount of the nail that is accelerating with its low mass. And so it moves much, much faster. So you don't even notice it. If you think I'm wrong, try taking that same hammer and smashing something like an anvil with it. I know, not everybody has an anvil, so maybe just a random piece of metal. You're going to see the hammer bounce back a lot more. And that's because when it has a lower mass, it will accelerate more than what it's hitting. But anyway, we call this a Newton's pair, a Newton's third law pair, because it's equal and opposite forces.